the two of them, I'm going to dress up in female clothes and get another one of them, which is a girl, to dress up in a guy's uniform and drag them around while I go trick-or-treating. I never thought I'd see the words minister and dad bod in the same sentence until yesterday.
Okay, so nobody's online today. That's good. Still have time.
Sometimes he's asking questions about what is this movie from? Okay, my roommate's very passionate. My roommate was in that class, in his statics class, where he was asking during COVID, so he was asking us online questions. He has never seen a movie in his life practically. I have seen way too many movies, or at least know how to do movies.
I had the same problem.
So he just pulled me along and was like, "Hey, what movie is this?" Oh, it's that movie.
I would just take a screenshot of the
reverse image.
search it in Google. Yeah.
Oh no, I would just have keywords like the spaces forever. I think have the domes. I'm like, it's that movie. I never even saw the movie. I'm good at keyword searching.
So that became a problem for a couple of us.
Yeah.
And so he would usually mention somewhere in his lecture where the thing was from. So
Yeah.
he had to write it down.
Some of the movies were just slash zero, honestly. Like,
I wouldn't know. I didn't know any of them.
His main thing.
yeah. Pretty good.
Dr. Sensei, I didn't even know.
I had.
I like them.
Pretty good.
We have suffered through a lot of courses.
Oh my lord. Those exams during COVID.
Do you have any
Oh,
questions before we begin? By the way, I have to remind you, everything is recorded. Yeah?
I can say that. That's free speech.
Anything you say is recorded and can be used against you.
Okay, sure.
Okay, so I guess you already know, but the homework of Unit B1 is postponed to Monday.
Thank you.
Thank you.
There are a few requests. Oh, you didn't know? Up to that. Well, if you didn't know, you have nothing to lose. You have homework done. You can enjoy weekend. Huh? Anyways, for those people, they don't have weekend.
I love being
Okay. So homework postponed are usually not going to determine until the last minute because it benefits both sides. For those who did the homework, of course, you can enjoy weekend. For those who didn't, you have to sacrifice weekend, but you can still do it. Okay. Anyway.
Now you have extra time.
Okay, so let's begin with today's attendance.
No.
Okay. Thank you.
Can you have a talk with Dr. Raj, please?
I remember in our section, Dr. Ag was like, "Oh, these problems are easy." And he thinks back to Wednesday where it took us 50 minutes to do one problem in class with his help.
Oh, yeah.
And that problem was super easy because it was
I got stuck
going
on
ahead sheet one direction up to it. And it was symmetric about both axes. So
Yeah, got it. Yeah,
that's why
no
it's
problem.
0.
We'll only need to be symmetric about one axis.
But that's the thing. Even with all those simplifications, it still took us 50 minutes for that one problem.
Okay, I remember
The
that.
weekend problem.
So
Yeah, in the beginning of the class, you thought you were going to get 3 problems.
yeah, and
From
then
my
you
class.
and then you get to the homework. It's like, not symmetric about any axis. And
Yeah, so
oh boy.
Don't-
This is gonna take 2 hours.
So today's discussion is still
It's
weird.
awful, but everything else is.
And I know it is challenging to introduce a mathematical function to represent flow field, and then knowing that, hey, this is actually not the real flow, something called model flow field ideal flow, which is we are going to simplify everything down to something we can never simplify anymore type of equation. Then in that kind of mathematical expression, flow behaves kind of weird. It's ideal flow. It's not the real flow. But we can mathematically analyze every detail. So that's the introduction of potential flow theory. So it's just to start discussion about potential flow theory today. So this is ideal, or oftentimes called potential flow analysis. Okay. All right. This is a very classic aerodynamic theory based on the circulation. So, in other words, you're going to mathematically solve the circulation of the flow field, assuming this is steady flow, this is incompressible flow, this is no body force, in other words, gravity zero, and then this is implicit viscosity is zero. On top of implicit, this is actually irrotational flow. Mathematically speaking, del plus B is zero everywhere, irrotational flow field. Okay. All of those assumptions, flow field become ideal flow. And oftentimes people call this potential flow. We're going to find out why this is called potential flow field. Okay. So let me introduce you two different kinds of mathematical function, which is very, very important for ideal or potential flow analysis, which is your project phase 2A and phase 2B. Okay. Phase 2A is going to be due right after unit B3. Phase 2B is due right after unit B4. Okay. So let me show you just a sneak preview of each phase 2A and B. You are going to deal with a flow field around circular cylinder. So uniform flow gets in. Uniform flow with magnitude B infinity flows in and then hit this body and then flow over it. This is flow over circular cylinder. Okay. This is such a simple flow field, yet it is going to provide us lots of detailed processes of mathematical analysis of this type of flow field. Important thing is you can analyze everything purely mathematical function. Okay. So we are going to introduce two different kind of functions. One is something called stream function. Stream function, we are going to use the lowercase, again, lowercase Greek character psi. This is called the stream function. Okay. So first of all, what is the stream function? What is the origin? Okay. So origin of the stream function is coming from this equation. Have you ever seen this equation?
Yes.
I think we derived this equation. What's that? Have you seen this equation? I think we derived it somewhere. Yeah, go ahead. This is equation of streamline on XY plane. You're seeing it, and then where did you get this equation, by the way? What is the origin of this equation? Take a look at that first page. Oh yeah, first page. Take a look at first page. Here we go. Okay, here we go. So this is the origin. The concept of the streamline can be described mathematically by line vector ds cross product of velocity is equal to 0 everywhere is the definition of streamline. This is a definition basically saying that the streamline is the line you can draw in space everywhere along this line, velocity is in the direction tangent to the path. Then if you apply this equation to the 3D Cartesian coordinate system, you are going to come up with the three equations of streamlines on three planes. I'm looking at XY plane equation. Okay. Okay, so this is the starting point. Okay. Robert, are you taking pictures of them?
Yeah.
I mean, I'm video capturing everything, right? You don't have. Do you need to? Okay. This is everything's video captured. Okay, so you don't have to. I mean, you can kind of concentrate on kind of thinking about what's the concept.
Okay.
Yeah. Okay. Anyways, just a reminder. Video is always available. So I guess you are taking pictures also video capture too.
Yeah.
Yeah. Okay. Nothing wrong with that, but again, you don't have to do that probably. So let's go. Let's go back and take a look at it once again. So this is the starting point. Okay. So this is the x-prime plane equation of streamline. Okay. So this is the algebraic function of x and y. And the important thing is this is the velocity's y direction component. This is the velocity's u direction component. Both of them are function of x and y, right? So you just basically try to integrate over the field of x and y. The result is you are going to come up with some kind of function of x and y can be determined and then set equal to constant c. So this function of x, y, if you set some kind of constant c, it is going to actually represent the equation of streamline. Do you understand what I'm talking about? There is an original function, something called stream function, function of x and y. If you set some kind of constant value, it is going to represent this line. Oh, this line is stream function psi equal to, I don't know, 5 line. So another line comes in. Oh, this is a stream function psi equal to 2 line. This is psi equal to 0 line, psi equal to -2 line, psi equal to minus. What am I talking about? You can draw bunch of equations of streamlines using this stream function, using MATLAB. That's what you're going to do in project phase 2A. Okay, so this is called stream function. So let this fxy, this is a function of x and y by the symbol psi over bar. Now this psi over bar is still there. Psi over bar is a stream function by the origin. However, oftentimes we can assume that it's incompressible. Okay. Where is it? Stream function. Okay, so here. For incompressible flow, psi over bar divided by rho is also a function called stream function for incompressible flow field, psi. Okay. So oftentimes we just use psi, not the psi over bar. Incompressible stream function. So if the flow field is compressible, in other words, density is a variable, you can still define stream function psi over bar, but you have to keep track of the change in density with it. Okay. So in order for you to have a stream function, the flow field do not necessarily be incompressible. However, oftentimes we assume incompressible to simplify. Okay, anyways. So that is the stream function. And then you feel weird because this is pure mathematical talk, especially for those who has a logic reaction for mathematical things. You feel very uncomfortable. I can tell by looking at Peter. He's very uncomfortable hearing those things. Well, but let's face it, this is math class you're taking right now. This is a mathematical function, stream function. Stream function is a governing function of a steady, okay, steady, nobody equals implicit irrotational flow field. You can define stream function psi over bar to govern the flow field. And then if it's incompressible, you can even define stream function psi to represent the flow field. Okay, so far? I know it's not okay, but let's move on. Okay, so by knowing psi equal to c, this is the equation of streamline. Okay. Okay. Next page. So this is the concept of stream function. Let's just summarize what it is. So psi equal to constant gives the equation of streamline. So in other words, how many streamline you want to draw in a flow field? Let's say 20 streamline I want to draw. You are going to come up with psi equal to constant. Let's say psi equal to 0, 1, 2, 5, 20 constants. Each one of those represent different lines called streamlines. You are going to do such a plot using MATLAB. Do you know what kind of plot is that? Contour plot. It's called a contour plot. Okay. Contour plot, you can define streamlines. Okay. Number two, the stream function can be defined in 2D flows only. In other words, like I said, each plane, x, y, x, z, y, z, you can define equation of streamline. So you can only do 2D things. Suppose if you want to draw three-dimensional streamlines, you have to do a projection from 3 planes to construct 3D image. Okay? If the stream function is given, the flow field can be described. This is quite important. Stream function, if you take a partial differentiation with respect to x and y, it is going to represent the velocity of x and y component. This is because the fact that, okay, stream function is always tangent to the velocity field. That's why. Okay. So this is 2D xy Cartesian flow field. You can determine velocity u and v, x component, y component. If it's 2D polar coordinate, velocity in radial and tangential component, you can determine by taking partial derivative of stream function. Okay. This is quite important. And then what is the stream function? It's just to find out dimension of stream function. Stream function is a mass flow rate per unit depth if it's compressible flow field. Okay. Now, difference in the stream function is delta psi. That is going to give you how much volume flow rate per unit depth you can have. Okay. So this is the dimension of stream function. This is the dimension of difference in stream function, delta psi. Okay. So stream function actually describes the how much mass flow rate or volume flow rate you have in the flow field also. Okay. Okay, so far. I know it's not okay, but let's move on. Okay. Next thing is a completely different type of thing. Rather than using stream function, you can alternatively actually can use velocity potential to do potential flow field analysis. Now here's the term potential flow comes in. So ideal flow field is oftentimes called potential flow field. Why is that? Because this is the flow field. You can define velocity potential as a mathematical function. If you can define velocity potential as a mathematical function, you can call that flow field potential flow field. Potential flow field means that this is ideal flow. You can even define velocity potential as a mathematical function. So what is the velocity potential to begin with? What is the origin? Okay. So velocity potential is, okay, basically says, if you take a gradient of it, so velocity potential is phi, mathematical function of x and y. Let's for a moment, hey, there's such a thing exists in the flow field. If you take a gradient of this phi, this is going to represent velocity field. This is the definition of velocity potential. So this is a mathematical function of field x and y. If you take a gradient, it is going to represent the velocity. What do you mean? This is a function potential to become a velocity if you take a gradient. You go like, what the hell are you talking about? Well, it's nothing real, it's math. Okay? So it's just mathematical definition of velocity potential. So this is a velocity potential. Now, interestingly, can we define such a mathematical function only if you satisfy all of those assumptions? If the flow field is steady, incompressible, no body force, implicit, irrotational. Actually, irrotational is quite important. Now, this irrotational is mathematical simplification assumption we just introduced here in like 2 classes ago. I don't know. Yeah, that's right, maybe. Irrotational flow field is this is the vorticity del cross B everywhere is equal to 0. That means you're going to purposely ignore rotation deformation effects due to viscosity. This is a mathematical simplification for irrotational flow field. But if you do such a thing, great news. For irrotational flow field, steady and incompressible, no body force invested type of flow field, you can actually define velocity potential as a function, mathematical function. That's what we call potential flow field. All right? So that's what it means. So let's find out. So this is irrotational flow field. If you take a curl of a velocity field, it's going to be 0 everywhere. This is called irrotational flow field, right? Irrotational flow. Okay? Now, this velocity B for such a flow field can be represented by velocity potential. Here we go. So you can just plug in del cross del phi is equal to 0. Okay? Del cross del phi is equal to 0. What do you mean? Do you have better expression for that? Have you ever seen this in calculus class? This is del square phi is equal to 0, isn't it? Or you can say this. Have you ever seen this? What is this? Anyway, so I'm not gonna tell those kind of things for a moment. You're gonna realize or find out. Oh, that's what it was. I'm kind of expecting that moment. Okay. Anyways, so this equation basically states that for an irrotational flow, there exists. Actually, you can mathematically define a scalar function phi such that the velocity is given by the gradient of phi. This is called velocity potential, phi. Okay? So what am I talking about? Obviously, if you take a partial derivative with respect to x and y and z, you are going to represent velocity in x direction, velocity in y direction, velocity in z direction, because that's the definition of velocity potential. Okay? So from actual, more common sense, okay, so this is the concept of velocity potential. Remember, psi equal to constant line gives you the equations of streamlines, right? Well, streamline is kind of physical sense. Okay, if you see a streamline, what do you see actually? Are you visualizing flow field by using streamlines? I think so. Because by looking at a streamline, you can tell the overall direction of the flow field. Okay. So let's say this is your flow field. Oh, okay. This is probably Cartesian XY flow field. You're going to define it using your MATLAB. X equal to, I don't know, minus 5 to 5, y equal to, I don't know, minus 3 to 3 or something like that. This is flow field. Next step you want to do, okay, so I'm going to put circular cylinder in it. Okay. And then, mathematically speaking, I want to find out governing function of psi of this flow field, flow over circular cylinder. This is a stream function. If the stream function is given, or if the stream function you can solve, and then you know the stream function of this flow field, you can use MATLAB to draw streamlines. How would you do that? You are going to set psi equal to some kind of constant. So let's say this is the line representing psi equal to 0, let's say. Okay. Well, what is the line psi equal to 1? Well, psi equal to 1 is probably this kind of line. Oh, this is a line, psi equal to 1. Psi equal to 5, what is it? Well, psi equal to 5 is probably this kind of line. Psi equal to 5. Psi equal to minus 1, oh, that's the other side. This is a line psi equal to minus 1. Okay, psi equal to minus 5 is something like this. You can draw any number of lines if you know psi, which is governing function of the flow field. Because you're going to basically set the constant value corresponding to psi, connecting the value of the same psi, representing streamline. This is essentially contour plot of psi in a 2D data field of psi. Question?
So are each of those functions the exact same? They're just set to different constants?
Function is a psi. These are the equations out of those functions. So this function creates a bunch of equations called equations of streamlines. This is called stream function. Okay, go ahead.
So then, if psi is only represented in 2D, do equipotential lines, since it can be represented in 3D, is that basically the same thing?
What is equipotential lines? So let's just talk about that first of all, okay? So similar to psi, okay? Suppose if you know phi instead of psi. So now you know the phi of this flow field instead of psi, okay? Because similar to psi, phi is also governing function of this flow field. You can draw a bunch of equipotential lines in the flow field. Similar to psi equal to z equal to constant. Let's say phi equal to 0 is, okay, well, this is the line, phi equal to 0. Okay, so this is phi equal to 0 line. What is phi equal to 1? I'm not sure. It's probably something like this. And then something like this. Something like this. What are those lines? Those are called equipotential lines. What do you mean by that? Equipotential lines and then streamlines are mutually perpendicular to each other. That's what it means. Okay? So you can draw streamlines or you can draw equipotential lines to visualize the flow field. Which one do you actually choose? Streamline actually tells you, okay, the direction of the flow because it's tangent. Now, equipotential line tells you, okay, this is the direction perpendicular to each velocity. Mutually perpendicular to each other. That's what streamline and equipotential lines are all about. So those are the two governing functions to represent potential flow field, ideal flow field. You can use it. Okay, go ahead.
So phi generates a bunch of equations. You set it to a constant, and then it generates a contour for that one value of phi.
That's right. Contour of the data field. That's right.
Right.
So you are going to compute the data field to represent the flow field because you're trying to analyze the flow field using 100% mathematical function. Go ahead.
So I saw you draw that box. Does that mean the phi and
Box is a flow field. You are going to define your own flow field. That is essentially mathematical data field. You want to represent your flow.
Yeah, I just wanted to ask if the phi and or the streamlines and equipotential lines are always going to be 90 degrees.
Mutually perpendicular lines will be drawn by setting phi equal to 0 lines and psi equal to 0 lines. So each lines are mutually perpendicular, yes. That's right. So this is a classic technique of like a very traditional CFD flow field meshing. Okay. In order to compute the flow field properties such as velocity, pressure, temperature, blah, 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 you're going to mesh up the flow field using streamlines and equipotential lines and then come up with node points. Those are the node points. Okay. Node points means at each location, you are going to compute the velocity, compute the pressure, compute the temperature, compute the density, whatever it is. So within the flow field, you have a knowledge for those node points. What are those values? then you can represent the velocity field or density field, pressure field, whatever. This is a field solution of flow field. Okay? That's the only thing you can do. This is called discretization or meshing of the flow field. Go ahead.
What is the psi or equals to -5 and psi equals 5?
That's some kind of constant. You can come up with any constants. You can draw any number of lines psi equal to, in this case, I try to draw psi equal to 0, 1, -1, 5, -5 lines. You can draw psi equal to 0, 0.1, 0.2, 0.3, blah, 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 like 100 lines, million lines, 1,000 lines. You can draw any number of lines by setting any number of constants. That's called contour line. Do you know contour line? Have you ever seen contour line? What is the example of contour line? Somebody please tell me. Go ahead.
Looking at a map with
Map.
elevation changes.
Map. That's right. Topology map.
Those things in Calc 3.
Here we go.
with those.
That's contour line. That is essentially streamline and equipotential lines. If you know the governing function of the flow field, mathematically speaking. So that's what we're trying to do. Okay? So I hope you get those things by going through projects. So this is the streamlines and equipotential lines to represent flow field. This is a visualization of flow field. And then very basic technique to come up with the nodal points. Nodal points are the only points you know the data. In other words, flow field properties can be known here, 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 here. So how fine your mesh is going to be how accurate you can represent your flow field properties. In other words, if somebody says, okay, what is the velocity here? You have no idea, because it's not node point. You can linearly interpret between those surrounding node points. That's the only thing you can do. That's quite frankly what the CFD is all about. Okay, finite element method, computational fluids, everything is just like this. You have a limited knowledge based on how fine your mesh is, right? That's why you have to match your model. Okay, question?
Couldn't you just add a psi equals 3 and a phi equals?
You can do that. You can add more nodal points, but you require a bigger computer for doing that. Oh, rather than 100 by 100 node points, you have to deal with 1 million by 1 million. Now all of a sudden your laptop is so small, you cannot do anything. Anyways, so that's what the CFD finite element method, it's essentially computer simulations are about. Okay, you're going to kind of step into those fields. Okay, now we have to do that because we can never do compute by hand of anything in a flow field, right? Okay, so comparing to this, structures is a piece of cake. Everything you can do it by hand. Think about that.
You shouldn't.
Yeah, you can do everything by hand. Structures, piece of cake. You can tell that to Dr. Lester. Dr. H said this. What do you think? Then she said, of course, that's true. Structures is piece of cake. Everything's deterministic, algebraic. Fluid mechanics is not. Okay, it's not at all. So this is one of those discretization techniques to discretize the flow field. You can only represent based on how fine your mesh really is. Okay. All right. So now we are going to get into ideal or potential flow field analysis. Okay. Velocity potential you can define for such a flow field. That's why it's called potential flow field. Ideal flow. Okay. Those are the assumptions. Steady, no body force, inviscid, irrotational because inviscid, and incompressible. And then what is the great thing about this velocity, which is, well, what's the good thing about this potential flow field or ideal flow field? What's the great thing? So this flow field is governed by one equation and one equation only, the Laplace's equation. Have you ever heard of it? What is Laplace's equation? Somebody please tell me Laplace's equation. What is it? Laplacian phi is 0. This is Laplace's equation. Okay. Or Laplacian psi is 0. It's This is the process equation. You can represent the process equation either velocity potential or stream function, either way. Now, in this class, we are going to purposefully use this one because it makes more sense. Because knowing the stream function, you can instantly draw streamlines using the tools such as MATLAB. Okay, so that's why we are going to actually use this one. But you can alternatively do everything based on the velocity potential. Some other professions field, like I don't know, space physics people, they may end up using velocity potential instead of stream function. Now, aerodynamics, stream function makes more sense, makes more physical sense. Okay. This is called theoretical error, very classic style. Laplace's equation. Have you ever seen this? This is called Laplacian, right? What is Laplacian? Have you seen this? Laplacian. Laplacian operator. Mathematicians need to invent this operator because you guys demand it. You are aero people. Needed to solve this equation. Of course, you're taking this class. You have to solve this equation using MATLAB, and otherwise you cannot go through this class. You cannot graduate. You have to solve this equation, the process equation. Okay. So this class is all about your attempt to solve the Laplace equation using software. X5 is ultimately saying X5 is trying to solve the Laplace equation. Xfoil is the software basically trying to solve the Laplace equation. Okay, that's where the theory comes in. Prandtl circulation theory, theory of aerodynamics. Okay. So let's take a look at next page. Okay. So next page, I'm going to kind of review what we've been talking about. Okay. So we are going to simplify our equations. Equation simplification process. Okay. What is the starting point? Okay. First of all, governing equation. Governing equation has been covered in Unit B1. Did you look at it? What kind of governing equation did you see in Unit B1?
Integral, differential.
Continuity and
Divergence.
yeah, continuity, momentum, energy, right? Those are governing equations coming from originally from fluid mechanics. You have continuity, momentum, energy equation coming from fluid mechanics. That is a combination of the governing principle plus Reynolds transport theorem gives you integral form of governing equation. Right? Now, integral form of governing equation can be changed into differential form of governing equation, and also substantial derivative form of governing equation. I think you saw those.
Yes. Yep.
Now, Unit B1, I purposefully completely ignore energy, because this belongs to someone. Aerodynamics, especially low speed, we purposely ignore the energy application. But at least you've seen continuity equation, momentum equation, x and y and z direction, right? In integral form to begin with from fluid mechanics, and then differential form, and then substantial derivative form, lots of forms. So let's just pick one of those. Okay.
Is substantial the addition of both of them? So you can just choose that one instead.
Okay, sorry?
Isn't substantial the addition of both of them? So you can just choose that one instead.
What do you think? Wait a minute. Let's go back to B1. Okay. Wait a minute. That's a very fundamental talk. Wait a sec. Did you look at the handout? Yeah, no, it's fine. But did you look at the handout? So this handout is probably one of the best I have ever seen. You know, I'm kind of self-appraising by myself. Wait a second. Yeah, you know, I made up this handout out of like an inspiration, and then one of my students graduated years ago. Now, this person is a researcher at Los Alamos. He's got PhD way back, and then he's now working at Los Alamos. And he said, well, this is probably one of the best explanation of the difference between integral form differential form, and substantial derivative form of three conservation laws: continuity, momentum, energy. Okay. Then I'm kind of started to self-appraise. Okay, oh, if you 6, cool. Because there's a PhD guy working at Los Alamos says so. Yeah, okay. So let's take a look at this. Is the governing equation from fluid mechanics is all about integral form. Of course, the origin here is Reynolds transport theorem combined with governing principle, right? Okay. So this is a continuity integral form fluid mechanics. And then this is same equation, just the aerodynamics form. So difference is Iowa State professors versus, John Anderson. Okay, so it's the same equation. Anyways, this is a momentum equation. This is not the single equation. This is 3 components in 3D space, right? So you can break down into 3 directional components in X, Y, and Z, right? Because this is vector equation. So why do we need to use vector equation? That's the big question here. We want to use it together with control volumes, right? So that you can hand calculate something flows in, and then how much change you expect within the control volume, and something flows out, everything balanced up. You can solve a problem in fluid mechanics. That's what you did in fluid mechanics. This is integral form of governing equations. I'm only listing conservation mass and momentum only. But now, you are seeing differential form in unit B1. Okay? Why do we need such a thing? Differential form is essentially you're going to put your eye on each and all particle that actually represent flow field. You can apply each and all of those equations for each and all of those particles. It's essentially equation motion approach. If this is a dynamics class of particle of only one, you can survive it. But how many particles do you think to represent flow field?
A lot.
A lot.
More than one.
More than one.
2.
More than 2.
Just
So
like
anyways,
one.
this is down to okay. So this is very, very good down to us. You can solve some practical problem, but this one is very accurate. But how can I use this to solve something? No, nothing. Right? This is like a physics people. Well, we come up with the equation. Our job is over. Now, engineers, you solve something. Then Reynolds transport theorem basically says, well, I can solve something if I come up with control volume. That's what you did in fluid mechanics. Okay, so now what is a substantial derivative? It's a combination for those 2 things to represent the entire flow field. Okay, so this is substantial derivative form. So please try to understand it. Okay. So you are going to represent full description of the flow field properties by using substantial derivative, inclusive of everything. In other words, in the flow field, okay, properties such as velocity can change over time and also can change over positions, both. You need to represent both. That's called substantial derivative. Okay. So having said that, this is handout, so please read it. Okay. So having said that, I'm going to pick up one of those equations here. Okay. So I'm going to pick up a momentum equation of x direction. Let's say x momentum. Okay. I'm going to walk through how can we simplify this equation, starting all the way from governing equation. So this is a substantial derivative form of x momentum. Rho substantial du dt. You guys know already what's du dt, by the way. This is substantial derivative of velocity u with respect to time. So this is, that's right. That's right. So this is du dt. So velocity in direction component x is going to change with respect to time. This is unsteady component plus u du dx plus b du dy plus w du dz. What are those? What's this? This is called time rate of change. This is a position rate of change. Velocity also changes in the different positions, even though it is steady state flow field. So this is local acceleration. This is convective acceleration. Okay, both of them are represented in substantial derivative. Please take a look at the handout, try to understand what it is. Okay, so this is going to be negative dp dx plus rho times fx plus fx viscous. So this is a complete description of x direction momentum equation. Go ahead, question.
Can we drop fx and f viscous because we're making assumptions here? Or no?
No, this is no assumption involved governing equation.
Okay.
So we're going to start applying assumptions to simplify.
Okay.
Okay, so first step assumption, of course, you want to apply, okay, assumption, steady flow. If the flow is steady, what happens?
du.
This term drops off.
Yeah, the local one.
This term drops off, right?
Yep.
And quite frankly, that's it. Okay, that's it. So flow is steady. So velocity is not depending on time, but all other component remains. And also this is x direction only, so velocity b is 0, velocity w is 0, those two drops off because directional sense, okay? That's it, yeah. And then let's apply a little bit more. Implicit, okay, implicit, this term drops off. Okay, what else?
Body force is ignored?
No body force. So body force is 0 means, okay, so that means, hey, I can now drop it, this one. This is the body force. So the result is, by the way, what kind of equation you get? Euler's equation, that's right. So Euler's equation in x direction, I hope you got this, right? You got that? U du dx is equal to minus dp dx. No, rho.
Yeah.
Rho, okay.
Okay.
Rho, okay.
Other question.
Is this what you get in your homework?
Yeah.
Yeah?
So
Actually,
when
it's-
we turned it
Oh, yeah,
into like
right.
we moved the dx over and all that stuff.
All that stuff? What do you mean? Be specific.
Okay, so
So this is Euler's equation in x direction, right? Now, I know what you're trying to say. X direction.
can we just say is the same for the y and z? Do we have to?
That's right. So you're gonna have a y direction Euler,
Yeah.
z direction Euler, everything's partial derivative.
Yeah.
Now, how can you express this into ordinary derivative such as dp is equal to minus rho b db? So this is ordinary derivative. This is essentially in the direction tangent to the path, you can say that, independent to x and y and z. So this is based on streamline coordinate system. You come up with the exact same thing. Those are the exact same equation. Do you understand that?
Yeah.
This is only in x direction, specifically x, y, z Cartesian. You have y direction, z direction, 3 equations of Euler in Cartesian x, y, z. This is a single equation in the direction tangent to the path given. Question, go ahead.
Do we like cross out the partial x on the bottom for any reason?
No.
Okay.
Again, please listen to me. These two are the same equation. It's just application-wise, it's a different coordinate system. That's what I'm saying. I just keep saying the same thing over and over. You cannot cancel out dx.
Yeah.
Your math teacher will kill you. You can never do such a math. No, you don't do that. Okay, well, I'm going to tell Dr. Tsutsu, you know, about he'll kill you. There's no such a math. Okay, go ahead. Question.
I was just gonna ask, could you combine all three with the gradient?
No. Combine all these 3 with gradient. Sure, yeah. That's the shorthand notation of 3 equations using gradient. Yes, you can possibly do that. But again, you just keep using x momentum. So one more assumption, incompressible. What do you get?
Bernoulli
Ah. Incompressible means density constant. Density constant, you can integrate along the path. If you do such a thing, of course, p plus 1/2 rho
Oh my
p
God.
squared is equal to constant. This is along a given streamline, okay? So this is something you used in Unit A3 trying to solve something, okay? Now, one more assumption here. What is it?
Energy,
Irrotational.
irrotation.
Energy, we're not going to even talk about it. Energy belongs to someone. From now on, we're not going to talk energy in aero, because this is low speed aero. If you go to high speed, you start talking about someone. Irrotational. Del cross B is equal to 0 vector. What do you have? This is the something called equation of ideal flow. You get equation of ideal flow by assuming irrotational flow field. What is it? This is called P plus 1/2 rho B squared is constant. Then you go like, huh? Well, this is like everywhere, not constrained.
In the entire field?
Entire field.
Oh.
This is called equation of ideal flow. So next class, okay, we stop here today. Next class, if this is the governing equation of ideal flow field, what can you actually say from here? This is called ideal flow analysis. Okay. So let's stop here today. Wait and see, we're going to have another equation shows up. In other words, pressure Cp is 1 minus B over B infinity squared. We're going to derive this equation next, starting from here, okay? All right. Have a great weekend. See you guys after Monday. Happy Halloween. Is that right?
Thank you.
Okay. Yeah, I'm gonna stop recording.
What?